Okay, so let's wrap up this module. So we saw in a preview, we talked a little bit about lifecycle processes, we talked about requirements, we talked about utilities. And I'm going to, at the end, the last couple of slides, I'm going to talk a little bit about the role of hardware and software within system, as well as aircraft-related issues. So we saw before, that a typically system engineering approach is hierarchical. So that means that you're defining a system, then you're going to, with associated requirements, then you're going to, during your conceptual design and your preliminary design, you're breaking the system up in a set of subsystems. And then your critical design, you're going to actually break each of the subsystems down in a set of components. Now, these components can be both software, SW, as well as hardware, HW, components. So if I, for example, look at this little avionics box, so this is referred to as a line replaceable unit, since you can actually take it in and out of the aircraft fairly straightforward as during a maintenance action. But you see, within this particular avionics system, you'll have maybe hardware components and software components. And typically when you deal with these components, there is standards out there like DO254, we'll talk about later, and DO178B, or more recently DO178C, that talk about what it is that you should be doing when you're developing software for such a component. Now, the motivation to actually take software very seriously in the develop is, if you look at, and these numbers are just ballpark numbers. So if you see the amount of lines of code that are being used, in aircraft, fighter aircraft, or even premium cars, you see that's a lot of code. And for some of these systems on board of these aircraft, the system is safety critical. It means that when it fails, it may result in a catastrophic. It may be a catastrophic failure classified system, which means that when it breaks, it may result in an accident, where multiple people get injured or die. Okay? So you see, it's very important when you have that much code that you do a good job of putting this code together, because of safety-related issues, because of the consequences of a failure of the software. Now, one of the standard, or one of the, if you look at complex aircraft systems, which are, nowadays a lot of aircraft systems are complex because they have both a very advanced hardware component as well as a very advanced or complex or big software component. Yeah. So what Society for Automotive Engineering, SAE, has published is what they call Aerospace Recommended Practice, or ARP, for the certification of highly integrated or complex aircraft systems for boxes that have both hardware and software. Yeah, so this ARP, for example, the one 4754, and I think this has just been, was like a year or 2 years ago, it's been updated to 4754A now. So it provides designers, manufacturers, installers, and certification authorities a common international basis for demonstrating compliance with airworthiness requirements applicable to highly integrated complex systems. So one thing I do on this particular slide, I kind of talk a little bit more. What do we mean by highly integrated? Highly integrated aircraft systems means that these systems perform or contribute to multiple aircraft level functions. If I say, well, this is my aircraft, and I identify a system on board the aircraft, that system may perform multiple functions. Okay? So if it does multiple things, we call that highly integrated. But its output may also be input to multiple other functions, in which case it's also highly integrated, because its output is being used by multiple other systems. That means when it breaks, it will affect these other systems as well. On the other side, there's also complex aircraft systems. And those are the systems whose safety cannot solely be shown by test, and whose logic is hard to comprehend without the aid of analytical tools. So you have to do a little bit more than just testing. You need to actually analyze it and review it in a lot of detail. Now, one thing that you saw before is I talked about the hierarchies being system, subsystem, component. if you look at ARP4754, this is actually, since it actually talks about aircraft, it says instead of system it uses aircraft function, instead of subsystem it uses system, and instead of component it uses item. Yeah. So what you're seeing is within an aircraft there's multiple, in this case X aircraft functions. Within a particular aircraft function there may be an amount like I systems, and within each system there may be multiple items, and each item of course may be hardware or software or both. Okay. So in a sense that's the kind of the components. So now one way of looking at it, and this doesn't really specify, say system, subsystem, component, because you can also say, well, for each function I say this is a system and then this is a subsystem. It kind of depends what kind of person or what kind of system you're developing. Alright, so if you look at ARP4754, it really talks about the system development processes. In a sense, the life cycle processes that we just talked about in this module. Well, this is also related to what we call the system safety process guidelines, which actually looks at the system safety aspects. How does a failure of this system relate to safety of operation of this aircraft? Yeah. So I'm developing a system that's defined in 4754. It must of course be complex or highly integrated. At the same time, I also want to assess classify the failure, more or less, of this system. Of course, at the same time, you say, well, this system will consist somehow of a hardware and software component, and so it actually directly says kind of that, okay, the hardware development lifecycle processes are defined in DO254, and the software development lifecycle processes are specified in DO178B, and of course, that's now DO178C.